Yeah. Okay, good. Oh, so PV equals nRT is our ideal gas law. And I put those terms in red because I just want to talk about those two terms. Why is it called ideal gas law? So a law, as we've noted in science, is just a summary of our experimental observations. So this PV equals nRT summarized what we saw in class, last class, and just what we can do every day in the lab. So it's a nice, simple summary of our observations. And as a Christian, I'm going to think about a law as just summarizing the everyday, ordinary way God has designed the world. I believe God's the creator, so I'm going to think of any scientific law as just an ordinary way that God has designed and sustains our world, according to our limited understanding, because our laws can, kind of just be good for some situations, but not others. So that's where the law comes. It's usually expressed as an equation. And ideal means, behavior of any gas, and it turns out it's really good under room conditions. We've specified room conditions to be SATP conditions. Hopefully you looked that up from last class. SATP. As soon as we deviate from SATP conditions, then PV is not so good. So when does PV not equal nRT? Well, at very high internal pressures, much, much greater than the SATP standard pressure, so much, much greater than 1 atmosphere. And this is because when you get really high pressures, you're really crowding those particles together, and there's just less space available for particles to travel around in, so they start repelling. And some particles can repel more than others. Size matters. The bigger particles, they're going to feel more repulsion, crowded into a smaller space than the smaller particles. So whatever volume is predicted by PV equals nRT, it's not going to be right. It's going to be affected. And then at low temperatures, the lower and lower temperature you carry out an experiment, lower than the standard SATP temperature, then the particles are going to get more lazy. They're going to move slowly. And as they do, when they do collide, they might stick a little bit. They're attractive. Intermolecular forces become important, right? Those dispersion, dipole, and hydrogen bonding forces can become important. They can stick a little bit. And if they stick, that's gonna slow them down even more, and they're not gonna exert as much pressure. So the pressure predicted by PV equals nRT is gonna be not so good the lower and lower the temperature that you go. So you kind of remember it this way. If you think of SATP as a perfect or ideal gas situations, the higher the pressure and the lower the temperature, the more PV does not equal nRT. So what do you do in those circumstances? Well, you can try to improve on this law to account for more extreme experimental conditions. And to do that, you're going to have to factor in the sizes of particles and their repulsions and the particular type of particle and their attractive intermolecular forces. So empirical parameters, that's based on experiment. It depends on whether you're dealing with hydrogen gas, methane gas, fluorine gas. It's all going to vary a bit. So that's going to add some complexity to the law if we're going to incorporate in some empirical parameters. So you can do this in different ways. One way to do it is what this guy named van der Waals did. He came up with an equation that's a little improvement on PV equals nRT, but there are other ways of doing it. I mean, actually a whole bunch of ways of improving on it, and some are good in some situations, some for others. So how does that work? So the van der Waals equation, I thought I would share that one. So van der Waals equation improves on PV equals nRT by trying to account, like if we just solve for P here, we bring the V over to the other side. And so P equals nRT over V. But if you subtract a little from the volume to account for particle size, this is number of moles. This is an empirical constant for size. And then if you take this whole pressure term and subtract that a little bit, using another empirical parameter, then that's going to help account for intermolecular force attractions. So these particular van der Waals constants, empirical constants, you can look up in databases. So it adds a little complexity, but it's not too bad. All right, so let's try an example. I'm going to do a series of examples. So example 1, we're going to look at a sample of a gas. And it looks like there's methane gas in there. Not that we can see it, but this is methane gas. There's 1.2 moles in a 3.3 liter container, big container, and it's at room temperature. So somebody's trapped some gas in there. And what are we supposed to do? Oh, let's just determine the pressure exerted by the gas on the interior of the container. I mean, you might want to know whether there's too much pressure being exerted, like maybe this container is going to have to give, or whether it's perfectly fine. We should do a quick calculation to see if that's a dangerous situation. So we're going to use PV equals nRT, the ideal gas law, and we're going to solve for pressure. So all we got to do is plug in our numbers. The moles is 1.2 mole. The R value, 0.0820 liter atmospheres per mole Kelvin. And then room temperature, that's SATP, that's 298.15 Kelvin. Always put it in Kelvin. Your answer will be wrong if you put it in degrees Celsius. And then the volume, 3.3 liters. So we can see in terms of units, mole and mole cancel, liter and liter cancel, Kelvin and Kelvin cancel, and that's going to leave us with atmospheres. That's comforting. So try putting it in your calculator, and you should get 8.9 atmospheres. That's a good amount of pressure. 8.9 atmospheres. I sure hope that particular container can stand that 8.9 atmospheres. And that seems a little high. So sometimes we worry about whether this ideal gas law is going to be good for that high of pressure. So maybe we'll do a quick calculation and we'll try the van der Waals equation and just see if we get a deviation. Because that's pretty high pressure, there could be a deviation. So we have to look up the van der Waals parameters for methane in particular. Kind of have really weird units when you look them up. You could use the NIST database, the government database. You could use the CRC Handbook of Chemistry and Physics. And if we plug all those numbers in, including these empirical parameters, and solve this thing and use strict significant figure rules, we'll get 8.8 atmospheres as our prediction from the van der Waals equation. So not a whole lot different. If your question is just, is this container going to explode or not, it doesn't matter which one you use. But if your research question was something where you really needed to know to more decimal places, needed something more accurate, you might want to go with the van der Waals equation. There's only like a 1% difference here, so it just depends on the question. For most of our purposes, we're pretty happy with PV equals nRT. Okay, so we'll go to the next video and we'll look at some conditions where we do a change on a sample of gas, much like last class.